So let's work through an example with the probability rules. What we're going to do is we're going to use the probability model from our dice example in the previous video to illustrate some of the probability rules. So the probability of rolling a sum of 5 would be the probability that I get a 1 and a 4 or a 2 and a 3, and then we switch the colors, right? So that's going to be 4 out of 36. So 1, 2, 3, 4, 4 out of 36, which I guess I should have simplified. That would make sense, right? For me to do that. 1/9. And this is because these 4 disjoint outcomes make up the entirety of the event roll a sum of 5, right? If I wanted the probability like roll a sum of 2, there's only one possible way that could happen, right? And that's with like 2 snake eyes. Or just, they call it snake eyes when you get 2 ones. So the probability of finding a roll not a sum of 5, so any of the other possible sums, 2 through 12, that would be 1 minus the probability I roll a sum of 5, which would be 32, 36, which would be 16 eighteenths or 8 ninths. Finite probability models are what we're going to talk about next. So one way to find the probability of an event is to assign a probability to each of the individual outcomes that will make the event and then add up these probabilities. The idea works when there are only a finite, so fixed and limited, number of outcomes. A probability model with a finite sample space is called a finite probability model. To assign probabilities in a finite model, you need to list the probabilities of all the individual outcomes. These probabilities must be numbers between 0 and 1 that add to exactly 1, right? Because the probability of all possible outcomes has to add up to 1. And the probability of any event is the sum of the probabilities of the outcomes making up this event. We know that to be true. That's one of our rules. So finite probability models are sometimes called discrete probability models. And statisticians often refer to finite probability models as discrete. So the first digit of numbers in legitimate financial records often follow a model known as Benford's law. So call the first digit of a randomly recorded record X. Benford's law gives the following probability model for X. So the probability that the first digit is 1 is 0.3001, probably it's 2 is 0.17, 0.125, 0.09, and on, right? All the leading digits have a different probability. So show that this is a legitimate finite or discrete probability model. Okay, that means we need to show that everything adds up to 1. So each probability is between 0 and 1 is true, and then when I add them all up, I do get 1. So this is a discrete probability model. Next, I want to find the probability that the first digit of a chosen number is not 1. So the probability not 1 is going to be 1 minus the probability of 1. That gives me 1 minus 0.301. So the probability the first digit is not a 1 is 0.699. Continuous probability models are a little bit different. So suppose we went to choose a number at random between 0 and 1, allowing any number between 0 and 1 as the outcome, right? So I could choose 0.1, I could choose 0.00078, right? Any number between 0 and 1. We cannot assign probabilities to each individual value because there's an infinite continuum of possible values. There are infinitely many numbers between 0 and 1. A continuous probability model assigns probability as an area under a density curve. The area under the curve and above any range of values is the probability of an outcome in that range. So we're going to use a uniform distribution because they all have the same probability of occurring, kind of. So we want to find the probability of getting a random number that is less than or equal to 0.5 or greater than 8. So here we've got less than or equal, and here we've got greater than. 0.8. So we calculate the area, right? So my height's 1. Let's go back. So my height is 1. Okay, so if it's and it goes from 0 to 1, so this area would be 0.5, and this area would be 0.2, because it's between 0, 1, and 0.08. So the total probability, when we add them together, would be 0.07. So this is our continuous probability model. We can also have normal probability models. We can use any density curve to assign probabilities, and the density curves that we're most familiar with now, after our last few chapters, are normal curves. Normal distributions are continuous probability models as well as descriptions of data. Like all continuous probability models, the normal curve assigns probability 0 to every individual outcome. I don't think that 0 is supposed to be there. Assigns probability to every single outcome, right? It fits our normal distribution. So the probability of getting something from like our mean and less would be like 0.50, right? Total area under a normal curve is 1. So this makes total sense to use a normal distribution. So if we look at the heights of all young women, we find that they closely follow the normal distribution. This makes sense. Height is something that occurs naturally, so it would fit a normal distribution. We've got a mean of 64.1 inches and a standard deviation of 3.7 inches. So what is the probability that a randomly chosen young woman has a height between 68 and 70 inches? Well, we're going to have to use our z-scores, I believe, right? So we want to find the probability between 68 and 70. So we're going to take 68, 64.1 divided by our standard deviation. We do the same thing for 70. We get the probability of between 1.05 is less than or equal to z, which is less than or equal to 1.59. So those are our z-scores. So we converted this to z-scores. So my z has to be less than or equal to 1.5, or my z has to be less than or equal to 1.05, right? So here we have our normal distribution, 64.1, right? I've got 70 and 80, so I need to find the area here. And I do that by taking their z-table values. So here's the z-table value for 80 or 0.159z, which is our standard score, minus our z-table value for 1.05, and we get 0.0910. So that's the area in this sliver, 0.0910. So that has a 0.091 probability of occurring. If we repeat this random choice many times, the description of values of x is the same normal distribution that describes the heights of all young women. We also have random variables. So a random variable is a variable whose value is a numerical outcome of a random phenomenon. Like we randomly generate variables. The probability distribution of a random variable x tells us what values x can take and how to assign probabilities to those values. A finite random variable has a finite list of possible outcomes, and random variables that can take on any value in an interval with probabilities given as areas under a density curve are called continuous. So we've got finite random variables and continuous random variables. The last type of probability I want to talk about is personality probability. So a personal probability of an outcome is a number between 0 and 1 that expresses an individual's judgment on how likely the outcome is, right? So for me, I'm traveling, so there's 0% probability I will see my cat. But there's like a 75% or 0.70 probability I'll eat a tomato because I love tomatoes. That's a weird example, Dr. Miller. Okay. To be legitimate, a person probably must obey rules 1 through 4 of probability, right? They have to take on a value between 0 and 1. They have to have independent outcomes, like the probability of 1 occurring and the probability of something not occurring like add up together, they still have to follow those rules. And it may not match another individual's personal probability of event. So like today, 75% probability I'll eat a tomato, but for you it'd probably be less. Maybe you don't like tomatoes, so maybe it's 0.